Hi everyone, welcome to our first training video in our series. In this video, we'll be going over how to use the Adib Robotics EtherCAT Master to control an EtherCAT servo drive, an EtherCAT slave. This is my hardware setup. On the far left, you could see the black box is an Intel Nuke mini PC. And to the right of that, there's a Yaskawa EtherCAT servo drive. And then there's a Yaskawa servo motor. You can see the yellow Ethernet cable connecting the Nuke mini PC to the Yaskawa servo drive. And then you can see the encoder and motor power cables connecting the servo drive to the servo motor. Here I'm on the Adib Robotics website. If you go to the downloads page, you'll be able to access some free trial software from Adib Robotics. In this video, we're going to be looking at the EtherCAT Master. There's an example code with the library for Linux, Windows, and Mac OS. The 2-hour free trial will run for 2 hours at a time, and then you would have to restart it. The licensed version does not have a time limit. So I'm going to go ahead and download the Linux library. I already have it downloaded, so I can access it in my downloads folder. Here you need to unzip it, and then I'm going to open it with Visual Studio. This is what's inside the folder. There's some ESI files for the slaves that you want to use. These are provided by the vendor. Typically, this is the one that will end up being used for the Yaskawa Sigma 7 EtherCAT servo slaves. This is a Linux real-time driver for the Ethernet connector. This is some optimization we did to run faster on Nuke mini PCs. It won't be used on PCs besides Nuke computers that use the IGC driver from Intel. This is the config file, and it contains the interface name. You can get that with ipconfig. Fconfig. It's called ipconfig on Windows. So we actually don't see this driver here because we're using the user space driver. So because this is a Linux machine running on Nuke, it will use the optimized driver, which is this one, and it doesn't need the interface name. But if you're running on Windows or Mac OS, or if you're running Linux on a non-Nuke machine, then you would need to update this accordingly. You will get prompted on the terminal if you did not select this properly. In fact, we might as well do that now. So if I tell it not to use the optimized driver, and then I set this erroneously to something that doesn't exist on this machine, it's going to complain to me. I'm going to launch a terminal here, and we have a convenience script called rebuild and rerun app that will allow you to rerun. It will build the example code, and it will run. So here you could see that you get prompted to select one of the network interfaces. This is the one that we're connected to. This is the physical LAN port on the back of the Nuke mini PC. So if I update this, then it will work. Let's take a closer look at the EtherCAT configuration. So this is the cycle time, and it's in microseconds. The minimum we support is 250, and that only works well on Nuke mini PCs running Linux with the prioritized user space Ethernet driver set to true. You always want this set to true because it means you would always prioritize the real-time driver. The cycle time only supports multiples of 250 microseconds. If you select anything else, it will tell you that that was invalid and it would pick the closest value. Yaskawa EtherCAT servo slaves do not support anything larger than 4,000 microseconds. This is the shift time. This is related to when the frame is sent relative to when a sync 0 event occurs on the slave. So you could see here there's a small diagram of the frames. This is sync 0, and then this is a frame cycle. And then you have this delay between sync 0 and when the frame becomes active. Usually you don't want to change this, and usually 30% of the the units are percentage of the cycle time. Usually 30% is good. And this is the receive frame timeout. If you have a low performance slave, you would need to increase this to the maximum you could. And usually we only support 1/4 to 3 times the cycle time. This is when the master, EtherCAT master library will say that the slave performance is bad and the frame was dropped, it wasn't received. So let's take a look at the main script. So this is an example C script provided by the download, and you can see that it natively supports Linux, Mac, and Windows OSs. The cyclic thread is the infinite thread that runs the EtherCAT cycles that occur synchronously. So here there's some real-time thread optimization that needs to occur initially. And then here this call is provided by the library that was provided, and the sleep will sleep the required amount of time until it's time for the next cycle to occur, and then it would transmit the frame, the EtherCAT frame, and it would read the data from the frame. It's reading the cyclic feedback data. At the end of the loop, we write the cyclic command data, we process asynchronous commands, we perform DC sync synchronization, and we receive the EtherCAT frame back. Because in every cycle you send a frame and then you receive it back. The processing of the asynchronous commands are things for like servo on and servo off, and the reading of COE objects and writing COE objects. COE objects are basically parameters on the slave, and servo on and servo off refers to the servo drive being in a mood that supports position commands and motion. DC syncs refers to distributed clock synchronization. All these devices have different internal clocks that run at slightly varying rates, and you need to continuously synchronize the clocks to each other. You either update the master clock or the slave clock, in which case it's called master shift or slave shift mode accordingly. Our EtherCAT library only supports master shift mode. It does not support slave shift mode yet. So here we have the main function of the C code. Initially we get the version of the EtherCAT master library, and then we initialize the EtherCAT master library. We do some system real-time pre-optimizations to optimize for real-time performance. We launch the cyclic thread. You can see here it's launched on Unix systems, and this is how it's launched on Windows systems. And we initialize the network, Initializing the network means we're scanning the network for slaves, and we place them all in operational mode. And then after this is completed, we're able to request operational mode. We're able to place all the EtherCAT slaves in operational mode. Once you're in operational mode, then distributed clock synchronization is running, and we're reading and writing commands to the slave. This API provided by the library gives you the number of slaves, and then here you can set the CIA 402 op mode. In order to be able to run in position mode, you need to set the slave in cyclic synchronous position mode, CSP. Here we read and write some CAN over EtherCAT objects, COE objects. So this is all just example code to show you how the APIs are used. This is the slave index. It's indexed from 0, so it's 0, 1, 2, 3. In our case, we only have one slave, so this is 0. This is the object index, object subindex, and the value that we are reading or writing. And now let's run this script. So this is the helper script to rebuild this file and run it. So here it launched the real-time Ethernet Linux driver, and you can hear the humming of the motor. It's because now it's servoed on, and you could see the motor slightly turning very slowly. It's because the update rate is slow, so we can increase the update rate. I'm going to stop the running, and then here we can see that it tells us that it found one slave on the network, and it initialized the sync manager information using the ESI file. So the ESI file contains information about the sync manager settings. Here it gives you the vendor ID and product code of the slave that it found. It tells you that it entered init mode, and then pre-op, and then it entered op mode. Here are the values read from the COE objects. And once you exit, it gives you some statistics about min, max, and current latency, as well as average and standard deviation. It tells you how many latency cycles ran, and then how many runtime cycles. And drift tells you the DC clock drift between the master and the slave. Also, you have current, average, min, max, and standard deviation. Now, we were running at 4,000 microseconds according to the config file, which is the default. But since we're running on a Nuke Mini PC, we can lower this all the way to 250 microseconds. And I'm going to set the receive frame timeout to 1/3 of that, so which is roughly 83 microseconds. The only values allowed are between 1/4 and 3 times the cycle time. Now if I run again, the motor is going to be running faster because we're adding 10 encoder ticks to each cycle, and now the cycles are occurring 4,000 times a second, because a 250 microsecond cycle time refers to 4,000 hertz, which is incredibly fast for an EtherCAT system, and that's only possible because we made some optimizations to the real-time Linux driver. This is where we add encoder ticks to the position. So anytime you have some slightly longer latency, you will get a warning, and it will print out these warnings. If you do some computationally heavy stuff, or you try to move the window too quickly, you will notice that it gets worse and worse. So you can see we've exceeded the maximum runtime, which is 250 microseconds. If I don't move the window around and if I don't do computationally expensive stuff and I run, I should be able to run successfully for long periods. We've ran stress tests for 2 weeks continuously with no issues. Potentially you could also close Visual Studio and run from the terminal. That would also decrease the CPU load and the amount of memory that's being used. So if I Control C now, you will see that the maximum runtime was 335 microseconds. Sometimes at startup there are some cycles that take long, but this should not be an issue so long as the standard deviation is very small. And here the maximum latency was only 5 microseconds, and here you can see the clock drift. The actual library file is this one. It's binary, and this header file provides all the APIs supported by the library, as well as some constants. So these are the APIs for COE reads and writes. These are for controlling the EtherCAT state, the mode in pre-op or op, and these are some of the other APIs we found in here. This concludes our first video. Thank you all for watching, and we'll see you next time.